Next, derivative of a function. So we know basic definition. The derivative of a function f of x is defined by f dash of x is equal to limit h tends to 0 f of x plus h minus f of x by h, right? So Fourier transform of derivatives of a function. So first result, we are going to see three results. So this is the first result. So the Fourier transform of f dash of x, that is derivative of f of x, is minus ip f bar of p. F bar of p is Fourier transform of f of x. So we know Fourier transform of f of x is f bar of p, which is equal to 1 by root 2 pi integral minus infinite to plus infinite f of x e power I p x dx, right? That is equation number 1. Now Fourier transformation of f dash of x, right? F dash bar of p, which is equal to 1 by root 2 pi integral minus infinite to plus infinite f dash of x e power I p x dx, that is equation number 2. We know that f dash of x is equal to limit h tends to 0 f of x plus h minus f of x by h, that is equation number 3. Using 3 in 2, we will get f Fourier transformation of f dash of x, which is equal to 1 by root 2 pi integral minus infinite to plus infinite limit h tends to 0 f of x plus h minus f of x whole divided by h into e power I p x dx. So that is taking the limit outside from the integral without loss in generality. Limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite f of x plus h minus f of x by h e power I p x dx. Limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite. So f of x plus h by h e power I p x dx. Then second integral, right? We are splitting into 2. So minus limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite f of x by h e power I p x dx. So that is equal to limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite f of x plus h by h e power I p x. We are multiplying e power I p x, right, minus e power ipx, because e power 0 1, e power 0 can be written as iph minus iph. So that is why e power ipx into e power iph minus iph dx. Minus limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite f of x by h e power ipx dx, right? So this is equal to limit h tends to 0 1 by root 2 pi integral 0 to infinite f of x plus h by h e power ipx. Now we are splitting the powers, e power iph into e power minus iph dh. Minus limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite f of x by h e power ipx dx. This is equal to limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite f of x plus h by h. So we are grouping ipx and iph, right? P is common, take it outside, e power I x plus h p into e power minus iph dx minus limit h tends to 0. This is nothing but f bar of p, right? Limit h tends to 0 f bar of p divided by h 1 by root 2 pi integral minus infinite to plus infinite f of x e power ipx dx is f Fourier transformation of f of x, that is f bar of p. So divided by h, right? Now this is equal to limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite f of x plus h by h e power I x plus h into p e power I p h. D of x can be written as d of x plus h. Derivative with respect to x, h is a constant, keeping h as a constant, minus limit h tends to 0 e f bar of p by h, right? So this is equal to limit h tends to 0 1 by root 2 pi integral minus infinite to plus infinite f of x plus h e power I x plus h into p derivative of x plus h into e power I p h by h minus limit h tends to 0 f bar of p by h. is equal to limit h tends to 0 e power I ph by h. Take it outside from the integral because integration is with respect to x plus h, right? So 1 by root 2 pi integral minus infinite to plus infinite, put x plus h as y. So f of y e power I y p dy minus limit h tends to 0 f bar of p by h, right? So that is equal to limit h tends to 0 e power I p h by h 1 by root 2 pi integral minus infinite to plus infinite, change the variable, right? F of x e power I x p dx. We know integral f of t is equal f of t dt is equal to integral f of x dx, which is equal to integral f of y dy. Change of integral, there will be no effect on that, right? The value are equal, right? Minus limit h tends to 0 f bar of p by h, right? So that is equal to limit h tends to 0 e power I ph by h, that is Fourier transformation of f of x, that is f bar of p minus limit h tends to 0 f bar of p by h. So f bar of p is common, take it outside from the limit. So limit h tends to 0 e power I ph by h minus limit h tends to 0 1 by h, that is equal to f bar of p limit h tends to 0 grouping, right? Limit is common, right? Common limit e power I ph minus 1 by h. It is equation number 4. So we need to find the value of limit e power I ph minus 1 by h. So consider limit h tends to 0 e power I ph minus 1 by h, that is equal to limit h tends to 0. So using L'Hospital rule, because when you are taking the limit h tends to 0, so numerator is e power 0 minus 1, so 1 minus 1 0, denominator is also 0 by 0 form. That is why to evaluate this we are using L'Hospital rule, some techniques, right? Limit h tends to 0, so first numerator derivative divided by denominator derivative, that is L'Hospital rule. So numerator derivative e power I ph with respect to h, right? Note that, right? So e power I ph is e power I ph into minus ip, then 1 is 0 divided by derivative of h is 1. So now taking the limit minus ip e power minus 0, so e power minus 0 1, so that is equal to minus ip. So using 5 in 4 we will get Fourier transformation of f dash of x is equal to f bar of p into minus ip, that is minus ip f bar of p, that is Fourier transformation of f of x, which is to be proved. Thanks.